So let's get started here. We are at the Center for Land Use Education and Research at the University of Connecticut. We are part of the College of Ag, Health, and Natural Resources, the Department of Extension, and the Department of Natural Resources, and the Connecticut Sea Grant. There are a number of programs that make up CLEAR, and they focus, all the programs generally focus on either climate change and land use, stormwater management, or mapping and geospatial technologies, which of course is our favorite here. So just a plug for our geospatial training program, where we offer hands-on trainings in GIS, GPS, and online mapping. Some of the software I'll talk about later, we do some training about it. So if it's new to you, you may want to check out the training program. Okay, so we're going to solve some mysteries today, I hope. First, we're going to talk a little bit about CT Eco and what that is. We'll do an introduction to Lidar, talk about the data sets we have here in Connecticut, and then some of the ways that we are serving this information to you. And then the second part will be using the information, the different layers available, the web pages that explain it, a viewer now that's nearing completion, and then finally how to connect to the data sets. And at the end, we'll talk about what's coming. So CT Eco, if you've not visited it, is a partnership between us here at CLEAR and the Department of Energy and Environmental Protection, and it is a website with the goal of providing multiple ways to access Connecticut's natural resource GIS data. So it's from very simple ways, like the map catalog, which are PDFs, to interactive viewers, to map services that can be used in your GIS, and to ArcGIS Online. So if you haven't had a chance to poke around CT Eco, please do so, and I'll show you the new Lidar section coming up. So we have a poll. Hopefully this will work. I'm wondering if you currently use Lidar. So I'm going to launch this poll, and you can use your mouse in the screen to choose one of these options. So if you go ahead and do that, about 29% of you use point cloud data, so I consider that to be pretty advanced. 38% of you use DEM tiles already. A good chunk of you don't use it yet, but I hope you will after this. And a few of you are just going to be educated, I think. Excellent. Okay, so back here. So what is Lidar? And what does it mean? So there are two different schools of thought. One is that it's an acronym for light detection and ranging, and that's where the word Lidar comes from. And another is that it's a combination of the words light and radar. So I'm not sure which is correct, or maybe both. But either way, it's a remote sensing technology that measures distance by illuminating a target with a laser and analyzing the reflected light. So here's another question. How do you spell Lidar? I had it there before, but then you would just say IT. So let's see, how do you spell Lidar? And here are our results. Most everybody likes it with just the little I, the majority, and then we have, it's very close between all capital and mostly lowercase, so that's pretty interesting. And I'll tell you why. Because I did a lot of research, because I really wanted to get this right, and I found that there was really no consistent way to do that, and even in some cases the same publication does it in different ways. So I don't know what's right or wrong. If you have a strong feeling or you know one is absolutely right, then please let me know. But I just picked one and went with it. So here's a second. Okay, so how does Lidar work? It's based on those discrete light pulses that are measured, their travel time is measured. It's a rapid collection of points that can be flown at night or in fair weather. And the result is a densely spaced network of highly accurate georeferenced elevation points, or this is what we call a point cloud, that creates the 3D representation of the Earth. So according to Kirk Waters at NOAA, who works with this information a lot, these scans are shooting between 100 and 200,000 points per second with about 10 centimeters of error, which is pretty phenomenal. So one of those laser pulses is pointed towards the Earth, and then parts of that beam are returned to the sensor on the airplane. And those parts are each called a return. So the first return is the first thing that gets hit by the beam, and then it goes through till the last return, which is usually or often the bare Earth. So then we kind of can get layers of information from these different pulses. And those layers in each of those points can be classified so that now we can pull out just those points that say represent the ground, which is a class 2. And that's what we're looking at here today. So I'm going to talk about some applications of LiDAR. This is from some of our own UConn folks that may even be on this webinar, where they are using LiDAR in New England for some archaeological applications, and it was highlighted in National Geographic. So that was a leaf-on aerial image where we can see a lot of trees but not much else. And we look at the LiDAR through that. You can see a lot of historic features like stone walls, building foundations, and so forth. So that's a great local application of LiDAR. It's being used a lot for flood mapping, for forest management and forest carbon, like how many trees, what their height is, width, standing volume of timber, and many other things for forestry. Vegetation and habitat mapping for all different uses such as crops, riparian areas, and even distance of trees to power lines. Coastal change and sea level rise is a good application for LiDAR because now we can begin to predict what areas may be affected. And I was approached a while ago about someone who was working on locating Nike missile sites. So if you look in the upper left corner on the aerial, it's difficult to see where that site might have been. The upper right is a grayscale historic aerial of that same Nike missile site. And you can see that in the LiDAR here, you can see where that missile site is really pops right out. So according to the National Enhanced Elevation Assessment, they listed a number of different applications that would have huge financial benefits from this kind of data across the country. And here are the top 10 that were listed. So I won't read them to you, but you can take a look at all of the applications. So hopefully you're convinced that this stuff is useful, and that's why you're here. So let's talk about what we have here in Connecticut. We have a patchwork quilt of data sets that are all colored differently on this map. And I'm going to talk briefly about each one. First, I want to talk about the difference between a point cloud and the grid cell data. So we had that poll where some of you said you used point clouds and some of you are using DEM tiles. And what is the difference? This is an aerial image of a neighborhood taken in the springtime. And here is a point cloud of the LiDAR of that same area. So hopefully you can see a lot of different points representing different elevations. If we zoom in a little bit, we can see how those points are spread across an area. And this is what the point cloud looks like in a flat representation. Now what we've done here and everything I'm going to show you today is that these points have been converted to grid cells, which we call grid or raster cells or pixels, so that now this is what we're working with, a gridded digital elevation model or DEM. So the most recent data set we have was captured after the hurricanes, after Sandy for coastal Connecticut by the U.S. Army Corps of Engineers and the USGS. And this has both the point cloud and DEM bare earth tiles were delivered. 2 parts of the state are covered by the New England LIDAR project, which was a project organized by the state of Maine and USGS and collected LIDAR data all along New England. 2 parts of Connecticut were collected and are shown here. They were delivered with 2-meter DEM tiles in point clouds. NRCS has done a lot of LIDAR collection in Connecticut. 2 parts, the nearly eastern half of the state and the northwest chunk are shown here, captured in 2 different years. FEMA captured the Quinnipiac River watershed, shown in blue here. No DEM tiles were delivered, just the point files. In 2006, FEMA collected some coastal Connecticut data, which we do use in a few places. Again, no DEM tiles were delivered, just the point clouds. So those are the main data sets that I'm using here today. There is a web page I'll show you in a bit that outlines each of these data sets and all of the specs that they have. They're all different. For each data set, I link to every piece of documentation that I have and that was delivered. It would be hard to write a metadata file because all of these data sets are different. Also on this web page is a link to where you can download. What you can download are the LAZ files, which are zipped LAS files or zipped point files from NOAA. So if you do go here and follow this link, it takes you to their download viewer, which allows you to pick the data set, the area, and then which data set and add it to your cart. So this is where you can download point files. On CTEco, we do not have any downloadable data, just different ways to access the data. Okay, so our goal on CTEco is to make the LiDAR accessible. I just showed you how you can download point files, but you need to know how to work with them, and you need to have GIS software. On CTEco, we're serving this in viewers, so it doesn't require any special software or know-how, and it does provide the ability to view this information with other data layers. So the way we're doing this is through map services. So generally, how are we serving this? First, I took those DEM tiles from the data sets that had them and put them into what's called a mosaic data set. For those two data sets with only last files, we use the last data set into mosaic data set and all of that into an image service using ArcGIS server. And finally, to you, a seamless digital elevation model. So the mosaic data set is a format that catalogs all the raster tiles and gives them geographic reference. It creates overviews, which are kind of different layers that make it draw really fast, and it allows it to be published in a fast, high-quality, easy-to-use format. So here's what we did. This is a mystery that we solved. Each data set has its own mosaic data set, which allowed it to have different settings because of all the differences. They were all added to there were some challenges. Here's the Quinnipiac footprints. Each of those is a last tile. And there were some problems when we first used that. We had some XY bounding problems. You can see those two tiles way off to the edge, which caused a real problem because the real data was only on the very left-hand part. And then if you can see here, we had some projection problems and data sets didn't line up, had to fix those. So we had a number of challenges, but eventually got all of those mosaic data sets loaded together into a single DEM data set. From there, we were able to apply what are called functions to create different types of layers. So here's just a look at the functions. There are some web pages that explain this in great detail, so I'm not going to talk about them now. So in the end, we have map services for hill shade, slope, aspect, shaded relief, and elevation. So let's talk about using these layers now and what each of them is. The first is the elevation. So this image here down at the bottom is a hill in Waterford, and I'm going to use this as a sample as we look at the different types of data. So the elevation is measured in meters, 0 to 700, which is about up to 2,200 feet or so. And this is what the elevation looks like of that hill. So of course the white areas are higher elevation and the black are lower. In the lower right corner there you can see the state where we put a colored ramp on it instead of a grayscale, so there are all different ways to look at elevation. The next is aspect. What is aspect? It's the direction a slope faces, or the orientation of the slope expressed in degrees. So if we take a look at a more colorful description here, we can see that north is 0 degrees and south is 180, and the colors that correspond to those different degrees around a circle or around a compass. So if you were to click on the aspect layer in the viewer, which we will do, you will get a degrees returned, and that degrees is associated with between 0 and 360, which are the degrees in a circle, or starting north and going around the compass. Okay, the slope map shows the rate of change of elevation. So the closer to white, or the closer to 90 degrees, the steeper the slope, and the darker the color, the flatter the area. So that's pretty straightforward. Hillshade is a grayscale view of the terrain that takes into account the sun's relative position. So the sun is described by altitude and azimuth to basically highlight and shade the terrain. So let's talk about that a little bit. Azimuth is the angle of the sun along the horizon. So this graphic shows you if the sun is at north, it's going to be lit up here on the top, and so forth around the compass. So in our case, we use an azimuth of 315 degrees, which is the northwest view. The altitude is how high on the horizon the sun is. So if it's at 90 degrees, it's directly above, and if it's at 0, it's right even with the ground. So we use 45 degrees in our hillshade. The shaded relief also uses azimuth and altitude to show a similar thing, except it uses a color ramp. to light up the features and to darken them. So let's take a look here. This is the new launch page for the Lidar website here on CT Eco. This will be linked to from the CT Eco homepage. I just want to point out a few things about the web pages, and then we'll take a look at the viewer and the data. So what is the elevation data? Describes each of those layers I just showed you. It also links to areas of more information. So on the left side here, we have Sleeping Giant State Park as a sample area. And on the right side is the portion of the Quinebaug River, that's a fairly flat area. So as we look through those areas on the different data sets, we can compare what you're seeing. Okay. I also showed you that page with all that data set information. Here's a link to that. This is an interactive map, so if you click on any of those areas, you'll get some of the key points about them. And if we scroll down, each data set has a table like this that links to all of the documentation that's available in different formats, FGDC metadata, so forth. And here is the link to download those point files from NOAA. And there, I put a little tip here about what you're looking for. Okay. I'll point out the frequently asked questions page, which is long and growing, of any questions that you might have about this. So this is just the start of this data set. We're hoping for feedback and suggestions and ideas, and this page will continue to grow as people ask questions. And then down here at the bottom is serving this data, which goes into more detail about what I mentioned about mosaic data sets and functions. So for you GIS techies out there, you might find this interesting. Okay, let's take a look at the viewer, which is the link right here. And give it a chance to load. Okay, so it opens up with the hillshade showing. First, to point out the zoom buttons and in and out over here on the left, so I can click the plus to zoom in, and we'll give it a second to draw. And then to pan this around, I left click and hold to drag this map, and we can see it moving around. There we go. And then the home button here will get us back to that initial extent of the state. Okay, probably the most useful button on here is the Layers tab, which is up in this upper right-hand corner. The first thing I want to show you is this Long Island Sound layer here at the top. Let me zoom in down here to the coast a little bit more. I'm also using my mouse wheel to scroll up. That's how it zooms in. And if you saw that coastal the water draw, you'll notice that here it's not drawn. And then when it draws, it makes a nice detailed shoreline. This data comes from NOAA, and the LiDAR data doesn't necessarily end right at the shoreline, so this is sort of a mask for visual purposes. If you don't like it, you can always uncheck it and turn it off, but it does make for a nice coastal view. Okay, let's go back to our extent here. The footprints layer shows what data set is being shown at every location. So there are some places that have 2 or 3 data sets at the same spot, and which one is being shown is important. So in this case, we have an overlap of the 2012 and the 2006, but if we click on this point, we will see not only is it the town of Groton, but that it's the 2012 data set that is being drawn on top. So this is important so you know which data set you're looking at and what year it was acquired. Okay, let me turn some of these off, and let's take a look at the slope. See what that looks like. Kind of a spaghetti map here. You can spend some time looking around at the slope. It's pretty interesting to look at. Okay, and the aspect map. This one shows the direction that the slope faces, so let's check out the pop-up. If I click on a slope, we'll see that this one is 308 degrees, so it was a very bright slope, northwest facing. If we do a darker slope, Oops. That is almost 30 degrees, so that's more northeastern facing slope. So that's how the aspect works. Let's take a look at the shaded relief. Give it a second to dry here. So here is our shaded relief, and I want to point out a couple of bookmarks that are saved. Oh, it didn't come up in here. All right, still working on this. Soon we'll have a bookmark for Sleeping Giant, which was that sample I showed you and what elevation data layers look like. So I'll give this a second to draw. And we will be adding more bookmarks if you have any suggestions of bookmarks that you'd like to see in the viewer.
Emily, while we're waiting for it to draw, Megan has a question. She's asked, have you noticed any significant differences in the quality or output of the different data sets?
There are some differences, but I have been using these mostly at a course level, so I haven't noticed them too much, but I'd be interested to see what others find. There are definitely places of overlap that don't line up as well as you might hope. Right. I think maybe everybody's on this and it's taking a little while to draw, so we'll give it a break here. Shouldn't take that long to draw. Okay. All right, and the last thing I want to show you here is this little arrow to the right of each layer in the layer list has a few little secret tools here. One is zoom to, which would zoom to the whole state. But maybe the most useful is transparency, so that you can make that particular layer semi-transparent. So making elevation transparent over aerials is a very powerful way to show data. So you can do that right here in the viewer. Okay, and while that's drawing, I'll point out at the bottom, it shows the XY coordinates in two different coordinate systems, WGS 84 Web Mercator, as well as Connecticut State Plane Nat 83 feet. So if you do find an area, like Megan said, that's either you see something wrong or maybe the wrong data set's drawing or something like that, note what those coordinates are and you can send us an email and we can see what we can do. All right, let's go back to the PowerPoint. So I have a question. In gridding the Quinnipiac River and coastal last files, did you perform bridge removal? Nope. No bridge, no water, no break lines. Didn't do anything like that. What is the aspect value for the flat areas such as lakes? That's a good question because some of the data sets had the water removed, so I would think it would be 0. I guess we would have to test that out. Okay, let's go back to the PowerPoint here. So I have another poll for you. How do you like to view geospatial information? Okay, so you can select more than one, and your choices are ArcGIS Online, ArcGIS Desktop, Google Earth, just in a web browser, you'd rather not use any fancy software, or something else. Unfortunately, I only had 5 choices to give you here. Okay, this is really interesting. I'm kind of surprised. We must have a fairly advanced audience here with 80% of you saying you like to use ArcGIS Desktop, which means you might have access to that, which is great. Google Earth was next, and then ArcGIS Online. No, let's see. The web browser beat out ArcGIS Online. So that's interesting. And those of you that said none or something else, maybe you can send me a message and let me know what that is. We try to make this as useful as we can for as many people as possible. Okay. So I'm going to talk about how to connect to this in 3 different softwares, which is why I just asked you, ArcGIS Online, Google Earth, and ArcGIS Desktop. So to use ArcGIS Online, which is a website put out by Esri for making and sharing maps pretty much, anyone can view a map, a public map, and anyone can save it, but you do need an account. There are 2 kinds of accounts. There's a free public account that does have restrictions, but it is free. And then there are organizational accounts, which come with your paid subscription to ArcGIS Desktop or you can just buy it. So that's another topic, but that's how ArcGIS Online works. So I suggest either two ways. You either start with our map and save it to your own account and then make changes, or you can start with a blank map and add our elevation data. So I'm going to talk briefly about each of those. So if you were going to start with our map, I put a link here and there's a link on the website. This graphic here in the lower right is a picture of the help page that exists, so if you don't need to be frantically taking notes, this is all written down on the website. Basically, you go to our map, you sign into your ArcGIS Online account, you can save a copy of our map to your account, and then you can change it. You can add some of our, remove some of our layers if you only want one or two of them. You can add your own, customize your pop-ups, and of course save it and share it. If you want to start with a new map, you go to arcgis.com and sign in with your own account. You click on Map, and then you add our data. How do you do that? In the Add Data drop-down, you choose Search for Layers, and you fill it out so it looks like this, a GIS server, and you type that in, ctecoapp4.uconn.edu, and you click Go. And once you do that, our different layers there show up, and you click Add, and now that layer will be added to your map. In ArcGIS Online, it looks something like that, and then you can customize away and save it to your own account. Okay, if you're a Google Earth user, which I think 40% or so of you are, what you need to do is get our KMZ, and there are two different ways to do that. This table here is part of this web page, so again, you can link right to them. The web page links you right to the KMZ file, or it links you to the REST endpoint. So I think many of you are ArcMap users, ArcGIS users. You maybe know what that is, which is also a way to get the KMZ file. Once you've downloaded that KMZ, that's where you get it there, you open it right up in ArcMap, and you're now connected to the different elevation services within Google Earth. Okay, using ArcMap, what you have to do is connect to our GIS server. So first thing is to go to Add Data, find GIS servers on the list, go to Add a GIS server. Again, these steps are outlined on this web page, so I'm just taking you through them quickly. Choose to use GIS servers, and then type in our server URL, which looks like that. And now that server is added on your list of GIS servers, and you can then get to all of the different map services or image services available and add them to your ArcMap document. In ArcMap, there are more options to change these data sets, and I'll talk about a few of them here, especially since many of you are ArcGIS users. So the first thing is symbology. The symbology tab of layer properties will look something like this for a grayscale layer, and here you can change all sorts of things. You can change the stretch, min-max, standard deviation, and some other ones. You can change the color ramp if you don't want it to show as grayscale. Certain stretches you can change the min-max. Like if it's a min-max stretch, you can change the high value and the low value. On the left, you can also see that there's classified and discrete color options if you're looking for a specific area. So you can play around with the symbology of the different layers. The display tab of the layer properties has this checkbox at the bottom to display the footprints. So these mosaic data sets are just linking to the tiles. Each tile has a footprint. There are many, many tiles in each data set. So if you want to see where those tiles are, checking that on lets you see that. So there's the choice to see all of them, which is what we're looking at here, or that second checkbox at the bottom, display only primary rasters. The primary rasters are the original tiles. The overviews are the rest. So there are many layers of overviews that allow it to draw quickly. So in this case, we're looking at all of the footprints, whether they're overviews or primary rasters. And in that case, we're looking here just at the primary. So let me flip through again. It's just a subtle difference. You can see a couple lines are removed. So that choice to view the footprints is under the Display tab. I also want to point out the mosaic options. So by default, all of our map services are being drawn using an attribute called BEST, which allows us to display what we consider to be the best data set on top on those areas of overlap. So that's what the default is, but notice you can use any of the attributes in the data set to order the way it's drawn. You can also use, not use attributes at all and use location to draw which tile is on top and then which operator. So there are a lot of options here for changing the way the data set looks. You do not have to go with the default that we have set. And a definition query is the best way to look at just one of the data sets. Maybe you're not interested in the whole thing or you want to just isolate. So you just use the query builder to build a quick query. And I suggest you do turn on those footprints because you're only going to be getting the primary rasters once you do a definition query like this. So I just did this one for the Coast 2012, and there it shows with its footprints. Okay, so just going to show you a little graphic here of an area. This is the Lidar and the aerial, and just to show the power of the transparency here. And this is, if you don't know, the Salmon River. This is the airline trail and the Lyman Viaduct, and here's the Salmon River. And here's a look at it in leaf-on imagery with the hillshade underneath. So the transparency is a really powerful way to show the data. Okay, let's talk about what's coming. This is a work in progress. We have a lot of fixes. For example, we, here's a look with the contours, and when we first were drawing this, we thought, oh, we cut the top of this mountain off, so we fixed the data range of that. We may find other things like this. If you find things, please let us know. It's an awful lot of data that's being served at one time. We are adding more information to the web pages. We will be adding additional viewers and welcome any suggestions or any sort of feedback. We also are happy that we are getting some new data to fill in this missing white area. This is what it looks like. USGS has coordinated this with some money from Hurricane Sandy. This data has already been acquired. It's a quality level 2, and it will have 1 meter DEM tiles along with the point clouds. And we hope to have it sometime this winter. So this will be a really exciting thing. We'll have quality level 3 or 2 data for the whole state. We would love quality level 2, but we would need to refly the 2 New England areas, the peach areas, and the blue areas to get to QL2 for the state. But regardless, we are going to have statewide coverage of LiDAR data, which is pretty amazing. We may be the first state to do that. I'm not sure, besides Rhode Island. So I went through that quickly. I can demo some things. If you have any questions, please send them in.
Emily, we have a question here from Meg. She wants to know what's the best way to use the point cloud data to understand return values on the points. Do you have a sense of that?
No, I really only work with the raster files. So there may be someone else on here that can answer the best way to use the point cloud data to understand return values on the points. You can symbolize the points in ArcGIS by return.
We have a lot of thank you Emily's coming in. I want to take a minute to give Emily lots of kudos. She's done a lot of hard work on this, as you can see.
Okay, suggestion to use the last data set tool in ArcMap. So yeah, if you're going to look at point data, I do know this, load those last files into a last data set, and then you can visualize it. In terms of the new LiDAR, I did just ask. We're hoping that by the end of this calendar year, it will be delivered, but it's in quality control, and so it's a little hard to predict. And then once we get it, we'll go through the processing. Did I lose my screen? Hold on. Go through the processing and try to get it up as quickly as we can. What's the difference between level 3 and level 2? Yes, I did not explain that. What's the best way to show you? I'm putting up a question about that, but it basically has to do with the point spacing and the resolution. So quality level 2 is a higher number of points, which results in a higher resolution output. Okay, somebody they had similar issues with the Quinnipiac data set. How did you end up filtering out the problematic points? I actually am an AirDAS Imagine user, and I opened those data sets up and did a subset to get the right bounding box for those files in Imagine, and then I was able to load them into the last data set and move forward. we can work together on that, or with other data. A PDF, a request for a PDF. We will post a PDF of the slides when we post the recording of the webinar, so it'll be on that webinar page on the CLEAR homepage, which is clear.uconn.edu. Okay, here's the web address for the LIDAR pages. It's cteco.uconn.edu/LIDAR, or on the CTECO homepage. There's a link right now in this news, and I will be linking it up to the rest of the navigation shortly. Okay, here's a question. Can you make DEM layers on different return values to show buildings versus trees versus ground? Yes, it's called a digital surface model versus a digital elevation model, and what it requires is that those points be classified so that you can pull out the points that represent surface. So some of our data sets have that classification and some do not. So I'm not sure that we're going to tackle that on a statewide basis, but it is something that can be done. Basically, take the last files into a last data set, use that return value or that classification, and then create a raster from that, and you get a digital surface model. For new users of LIDAR or new GIS users, why should we care about using LIDAR? What are the benefits of using LIDAR? Well, if you need elevation, it's really the best resolution elevation data that we have by far. So I showed a bunch of the different uses and applications early on. So, you know, water is a big one because water flows downstream. We're using it here, or downslope, I mean, using it a lot for flow, watershed delineation, that kind of thing. But there are many, many different uses of LIDAR. Okay, I think that does it for our questions. I'll put our email addresses back up here for a second, and please send us any other questions or comments. Thanks for joining.